Okay, a domino falls 8 block widths being the width of the concrete blocks that make up some of the walls in here, in half a cycle of a certain pendulum. So what's the acceleration of that pendulum? Of course, the domino is dropped from rest at the instant the pendulum crosses its equilibrium point, as best I could synchronize it. So, well, we calculate the acceleration. Average velocity is going to be 8 block widths divided by half a cycle, 16 block widths per cycle. Initial velocity is 0, assuming v versus t is a straight line. We get Vf is 32 block widths per cycle. So the acceleration is the change in velocity, which is 32 block widths minus 32 block widths per cycle minus 0 block widths per cycle, divided by the half cycle time interval, giving you 64 block widths per cycle squared. In the next problem, we're asked to take this result and convert it. Now, we could go all the way back to 8 block widths and convert that at 20.3 centimeters for every block width. That's going to be, what, 162.4 centimeters. And if a cycle is 0.95 seconds, then half of that, I think, is 0.475 seconds. And we could redo this whole calculation. Instead, we simply take this result and convert block widths to centimeters and cycles to seconds. So block width is 20.3 centimeters. A cycle is 0.95 seconds. So we can replace block width with the 20.3 centimeters, the cycle width 0.95 seconds, and do the calculation, and we end up with something in the neighborhood of 1,400 centimeters per second squared. Now, of course, all this relies on me being able to synchronize, to drop the domino exactly when the pendulum passes its equilibrium point, and to correctly observe that the pendulum has come back to its equilibrium point, but at the instant the dominoes hit the floor. There's a significant amount of uncertainty in that. I would say there's a 20% uncertainty in the measurement of in the observation of the time interval as half a cycle. There is not much uncertainty in the measurement of a block width. Those things are laid pretty consistently with an 8-inch difference, and 8 inches is 20.3 centimeters, up to the nearest, rounded to the nearest millimeter. Okay, so we expect there's a significant uncertainty here, and if there's a 20% uncertainty in measuring the cycle, there's going to be over a 40% uncertainty in calculating the acceleration, since you use that 20% uncertain result to calculate the average velocity, which gives you the final velocity, which still has that uncertainty, and another approximately 20% here. It mounts up. You could get as much as a 50% uncertainty out of it, or close to 50% uncertainty out of a 20% uncertainty in the cycle, a 50% uncertainty in calculating the acceleration. So we could easily be off by quite a bit here. The actual result, as you should know, is about 1,000 centimeters per second squared. And more precisely, 980, if you want 980.1, but we're at some altitude here, and you really don't know what it is at this altitude. So 9.8 and 980 is probably closer than whatever approximation you're using out of your textbook. Okay. And we can calculate that later using Newton's law of universal gravitation and assuming some sort of uniformity in the mass distribution in this vicinity. Okay, well, net force then, well, okay, this is completely different. Okay, that's this question and this. So this is a measurement of the acceleration of gravity. It's not an overly accurate measurement, but it is a measurement. Had I used a shorter pendulum 4 times shorter than the one I used, that would have been pretty short, but we would have gotten twice as many cycles. So we would have had a full cycle, and we would have been in better shape to observe small discrepancies in our time interval. We would have had a more accurate measurement of the time interval, but with the pendulum I used, we got a reasonable estimate. Of course, they're more accurate timing instruments. You could time this with a stopwatch, which might be more accurate than the pendulum, but I don't think so, because it's hard to measure a fraction of a second using a stopwatch. We could do this with electronic timing and get actually a pretty good result. And of course, there are other ways of measuring the acceleration of gravity, one being just to count a pendulum. But we don't know how to relate that right now. I could give you a formula, but until we derive it, I really don't want to give you that formula. Okay? So, there we go.